speaker of today is Leonardo Novo, and the topic of his presentation is quadratic speedup for partial search by continuous time quantum walk. So thank you, Leonardo.
Thank you, Alessandro. Thanks everyone for being here. You can hear me well, right? So yeah, thanks Alessandro for contacting me to give this talk. I hope it's interesting. So yeah, I will talk about this recent work, which was posted on the arXiv in December last year, with Simon Appers, Shantanu Chakraborty, and Jeremy Rollin. So all these people were at ULB at some point, but now Simon moved to Paris, Shantanu is in India, and Jeremy is still at ULB, and me. And I'll probably leave in a couple of months. So the problem is the searching marked nodes on a graph by quantum walks, in particular in the continuous time version of quantum walks. So I'll give you a little bit of an overview of the problem, the different approaches used to tackle this problem, both in discrete time and continuous time. So yeah, let me start. All right, so the structure of my talk is the following. First, I will talk about a first approach to solve this problem, which is a very simple, neat approach by Childs and Goldstone. Then I will talk about the limitations of this original approach and basically about build up on the tools needed to come up with our recent result, which improves upon the performance of this first approach for this spatial search problem. So I'll start with a very general statement. So first of all, as probably all of you are familiar with, there are different models of quantum computation. The usual one people consider is, let's say, the digital model where you have quantum gates and qubits and so on. But there are also analog models, for example, interacting spins, or a model which is like basically a particle doing a quantum walk on a graph. These are also universal models for quantum computation. And these analog models, okay, they obey the Schrodinger equation, and the time is now a continuous parameter. This Hamiltonian can either be time independent or time dependent. For example, in the adiabatic algorithms, the Hamiltonian changes slowly in time. And if it's time independent, we have this simple solution for the Schrodinger equation, right? So what is the motivation to study analog models? Well, for me, I think there are different motivations. One of them is, okay, we want to understand what is the computational power of simple offline models inspired by the dynamics of physical systems. Also, analog models, I believe they give us different intuition to come up with quantum algorithms. For example, adiabatic algorithms, I guess, which now, for example, give the intuition to develop variational approaches such as QAUA, etc. So they give us different intuition to come up with quantum algorithms, and often we can translate analog algorithms to the circuit model. So there are very general techniques to simulate Hamiltonian evolution in the digital, the usual circuit model quantum computation. So we can often translate any algorithm that we have developed in analog models to the discrete time, so to the digital approach, quantum circuit model. Okay. So as the title of my talk says, I'll focus on continuous time quantum walks. And again, as a general motivation, there have been some famous algorithms developed in this framework. So I'm going to focus on search problems on graphs. So we have a graph and we have a marked node, and we want to find it as fast as possible. But there have been other famous algorithms, for example, evaluation of NAND trees or exponential speedups for traversing graphs. So a famous result by Childs et al. And as I said, this is also a universal model of quantum computation, also proved by Andrew Childs in 2009. So a particle walking on a graph of exponential dimension is a universal model for any computational n-qubit. All right, so let me define first the classical case. What is a continuous time classical random walk? First we need to define what is a graph Laplacian. So graph Laplacian is constructed from the degree matrix and from the adjacency matrix. So the degree matrix is a diagonal matrix where each diagonal element is the degree of the vertex. So it's the number of edges that connect to that vertex. Okay. And the adjacency matrix, very simple. So it's a matrix that has ones if the ij's entry is an edge of the graph and 0 otherwise, okay? So it's a matrix that encodes the connectivity of the graph. We're gonna consider only undirected graphs. So this is going to be a symmetric matrix. So aij equals aji. And so in a classical case, we can write a differential equation for the probabilities of occupying a given node in the classical random walk. So it's a simple linear differential equation on the probabilities that depends on the Laplacian matrix, okay? And so on some real parameter that can be seen as the rate of propagation of the walk on the graph, okay? And so, as I said to Alessandro in the beginning, feel free to ask questions if something is not clear. So this matrix, as I said, is symmetric, and this equation conserves probabilities. Now, in a quantum case, we have the Schrödinger equation, and so the idea that was proposed even before this work, but it was used in this work of spatial search by quantum walk, is to choose the Hamiltonian to be proportional to the Laplacian of the graph. Okay, and now we have a very different dynamics because we have an equation, differential equation on the amplitudes and not on the probabilities. Of course, we have here a factor of I that comes from the Schrödinger equation minus I. And yeah, so we have the time evolution now is written like this, where gamma L is the Hamiltonian that determines the dynamics, right? So just to compare the two, here, of course, we don't have this factor of I, and yeah, so we have an equation on the amplitudes and not on the probabilities. Okay, so of course, this generates very different dynamics, so you probably are familiar with this sort of plots. So in the classical case, if you have a random walk on a graph, after some steps, is sort of a Gaussian probability distribution or a binomial probability distribution centered around where the walk started. In the quantum case, we have this quadratically faster propagation, and the propagation is like a wave, right? So this is in the 1D. Now the question we're going to look at is how can we use quantum walks, in particular in continuous time, to find a marked node on a graph, okay? So the approach that was proposed by Charles and Goldstone in 2004 is quite simple. So we have the Hamiltonian to be gamma times L, which is the continuous time quantum walk, as I just mentioned. And now we need an oracular part to the Hamiltonian that is able to identify the marked node. So here they just consider, and by the way, for the moment I'm considering just that there is a single marked node on the graph. And so here they consider a very simple approach where you just have a one-dimensional projector on this marked node, okay? And so the idea is that now can we, the only free parameter of the problem is this gamma. So the idea is, can we find a right value of gamma to somehow make the dynamics localize in this marked node? So usually you start like in the Grover's algorithm, you start with equal superposition of all the nodes of the graph. And you want to use this quantum dynamics to localize around the marked node, okay? And so gamma is this only free parameter. So they've shown, okay, so in a quantum case, we have a little bit of an ambiguity because we just need the Hamiltonian to be Hermitian. So before we needed the Laplacian to conserve probability, okay? So there's somehow a stronger restriction. Here we could consider both the Laplacian or the adjacency matrix. So these are both valid quantum walks, okay? So it's just a detail. But so Charles and Goldstone in their original work, they show that you can have optimal quantum search on different kinds of graphs. By optimal, I mean that you can find a marked node in a time that is square root of the number of nodes, okay? So it's similar to like a Grover-like speedup, but now in a sort of structured search problem. And so they've shown that this is possible in a complete graph, hypercube, and lattices. But for lattices, the dimension has to be sufficiently large, so the dimension larger than 4. So I already see some sort of limitation here. And so there have been a lot of subsequent works analyzing this Charles and Goldstone approach in different graphs. Typically, the approach was graph specific. So they had to analyze all these problems individually. There are other papers that I'm not looking at. not referring to here. But so in this work, for example, or I'm part of, we showed that the algorithm is optimal on random graphs, on Erdős-Renyi random graphs, as long as they are sufficiently connected. So one of the things that came out of this work was that we sort of need, if we have large spectral gaps on our graph, so spectral graph means like the difference between the largest, well, it depends on like the ground state and the first excited state of the Hamiltonian. So if a large spectral graph, this is a sufficient condition for optimal quantum search. So I won't go into details of this work because I want to talk about a more general work that we have done in 2020. So yeah, so here the general question is, okay, how can we obtain more general sufficient conditions for optimal quantum search? And so in 2020, with Shantanu Chakraborty and Jeremy Rollin, we look at this problem and we develop more general sufficient condition that were able to reproduce many previous results about optimality. So here, okay, we have our search Hamiltonian, again, this one-dimensional projector on the solution state, and we have this gamma parameter, and we have here what we call a normalized Laplacian, but it's very simple, so we just normalize the Laplacian matrix by its largest eigenvalue, okay? So if these are the eigenvalues of the normalized Laplacian, they are between 0 and 1 by definition, by the normalization. Sorry, this lambda n is this lambda max. And this, yeah, this should be equal to 1. So these are the eigenvectors. This is the solution. So the spectral gap is then the second largest eigenvalue, because we know that the first, I mean, this is a property of the Laplacian. We know that the ground state energy is 0. And we define this quantity. So it's not very important, the details, but it was useful to define these quantities that have to do with overlaps of the mark node with the eigenvectors of L. And here, these are the eigenvalues of the normalized Laplacian. So, okay, so this is just to introduce some notation. And what we've shown is that if the spectral gap scales as larger than 1 over square root n, this actually simplifies the condition on the spectrum. We have a more complicated one, but let's stick to the simple one. If this condition holds, then we're able to show what is the optimal performance of the, what is the best possible performance of the Charles and Goldstone algorithm, okay? So this means that we're able to predict what is the best possible value of this gamma parameter. As I said, this is like the rate of propagation of the quantum walk, which is given by this S1 quantity. And we're able to show what is the best time to stop the walk. So we have the largest amplitude at the solution. So this is given by these quantities. And so we are able also to predict the success probability if we stop the walk at this time, okay? And so if you see from these conditions, we can sort of derive conditions for optimality. For example, if this factor here is order 1, then we have the running time of square root n, right? And also here, if you see, this is just sort of the inverse of this squared. So if we have S1 squared by S2 of order 1, then we have optimality, okay? As long as, and this analysis was only valid here because we need to do some perturbative approach that assumes this. Otherwise, we don't really know how to treat the problem. Okay, so just to summarize this work before I go to the more general work, so we provide certain spectral conditions on L. So provided that certain spectral conditions on L are satisfied, we can predict the best possible performance of this algorithm, like the Charles and Goldstone algorithm. So we have derived the new sufficient condition for optimal quantum search. So at the time of writing of this paper, we're able to reproduce all previous examples of optimality. I don't know if this is still true. And so it's written like very simply in terms of these quantities S1 and S2 that I defined in the previous slide. But we also show that there are sort of highly symmetric graphs and well-connected graphs for which we cannot have a quadratic speedup. So an example that we give in the paper is the Rook's graph, which is the graph that has to do with the possible movements of a rook on a rectangular chessboard. So the rook can move like to any of these columns or any of these rows. So this somehow defines the graph. If you think of each square of the chessboard as a node on a graph. And we've shown that for certain proportions of the chessboard, we cannot have a quadratic speedup. So this is a new limitation of this algorithm that we kind of revealed. So new examples of where we cannot get this general quadratic speed. Okay. So so we see that there are some limitations of this approach. Let's try to come up with some more general things. So what is the general problem that we would like to speed up and that people have been working on in different approaches like discrete time, adiabatic, etc., as I'm going to tell you later. So the general problem is the following. We have a state space of, let's say, a Markov chain, X. We have some set of marked nodes M, let's say the red nodes here. And we have some set of unmarked nodes, okay? So the complement of the set X without M. Now, let's consider an ergodic reversible Markov chain P when there's Pxy. So it doesn't really matter the definition here. I'll just tell you what is the property that I need to use is the fact that P is a unique stationary state pi, okay? So let's say this is a well-behaved Markov chain. And so the classical algorithm that we like to speed up is very simple. So we generate X according to the stationary distribution, pi. So this is an assumption that is done in several works. Now we check if X is a marked node or not. So we assume that we have an oracle that's able to identify.
I have a small question exactly about this assumption. Can I read this this thing as like as a state preparation problem?
You mean like the first?
Like, okay, in the quantum setting, you prepare a state ket pi, no?
Exactly. Yeah. So in a quantum setting, you need to assume that you have this this ability. Yes.
And how do you know?
Some cases could be hard, huh?
Hmm?
Yeah. So this is an assumption. I guess in some cases this would be possible. In some other cases, this could be complicated. But your algorithm will take into account this cost as well.
Yeah. Yeah.
Right.
But basically, this ket pi is, you know, a left eigenvector of P.
Yes. Yes. Yes.
And
so I guess in the classical case, you could allow your Markov chain to mix and then run the search algorithm first. I guess in the quantum case, we could maybe do something similar, like do some sort of quantum mixing. But it's definitely a cost that needs to be taken into account. That could be large.
But so, so what is the kind of access model that you assume on the graph? Like, I mean, why spatial search? Like,
yeah,
what is the meaning of spatial?
It will be clear when I define like the Szegedy walk, but basically, yeah, I think it will be clear in the next slide. Maybe we can come back to this question.
Okay.
When I define the Szegedy walk, and let me know if it is working. Okay. So in the classical problem, it's very simple. Like we generate according to stationary distribution pi. We check if we find a solution, we can exit the algorithm immediately and output the solution. Otherwise, we just update X according to the Markov chain P, and then we check again and so on until we find, right? So the expected running time of this algorithm is called the heating time of the Markov chain P for a set of marked nodes M. And what we would like to achieve is can we obtain a quantum algorithm that runs in square root of the heating time? Okay, so we can want to obtain a quadratic speedup for this general problem. And so, as I mentioned, like there are some limitations of Childs and Goldstone approach in the continuous time quantum walk case. So, first of all, there are no general results about the performance for multiple marked nodes. There are some slightly general results for a single marked node, as I mentioned, but there's still open questions even in that setting. So, as I also mentioned, for some graphs, the algorithm does not provide a quadratic speedup with respect to classical heating time. And it's not even clear how to define a continuous time quantum walk. For example, if P is not symmetric, like P itself cannot be a Hamiltonian. So yeah, there are some limitations of this approach. So let's go to the bigger picture and let's consider now other approaches. There are approaches involving adiabatic algorithms, discrete time quantum walks, and continuous time quantum walk. Okay, so if you are at around like 2019, this was more or less the status of the matter. So there was an adiabatic algorithm that was defined for any ergodic reversible Markov chain. It provided a quadratic speedup for single mark node. And there was some performance guarantee for multiple mark nodes, but in terms of a quantity that was called the extended heating time. But this is not a general quadratic speedup. So this extended heating time can be significantly larger than the heating time. And there was this open question whether we have this general quadratic speedups even in the case of multiple mark nodes. Okay, so there was also a discrete time quantum algorithm for this, and the Childs and Goldstone approach has all these limitations that I have already mentioned. Now, until around 2020, we were working on this problem, and we were able to sort of convert the adiabatic algorithm. I mean, convert not literally, but we use a lot of techniques in the adiabatic algorithm to come up with a continuous time quantum walk algorithm that was able to fill these three boxes. It was still an open question about quadratic speedup for multiple mark nodes until, well, which was until the work of Ambainis et al. That was published, was put on the archives a few months before our work. So they were able to solve this general question of obtaining quadratic speedup for multiple mark nodes using discrete time quantum walks. So, and the work that I'm presenting today is to fill in this gap and have a continuous time quantum walk algorithm that also is able to provide the quadratic speedup and having a similar performance here. So there's no literal translation without there's no known translation between discrete time quantum walks and continuous time quantum walks without overhead. So it's not a trivial, it doesn't follow directly from here that we can have an algorithm there. So we need to do a little more work. All right, so yeah, so I'll just mention like what were the main techniques that were used to come up with this result in 2020. So there are other works in between, but I'll just mention what I consider to be the main big steps. So first, Szegedy defines a way to quantize a Markov chain. So to define a unitary operator for a Markov chain P. And he's able to solve the detection problem quadratic faster than the classical heating time. So what I mean by detection problem is like you're able to detect whether there are marked nodes or not, but not to find them. Then later, or quite later, there was the work of Crovy-Magnès, Zuzod, and Roland that uses the Szegedy walk and introduce a new idea, which is an interpolated Markov chain that I'm going to talk about a bit later. So it's basically, you can see it as a semi-absorbing Markov chain. And using this technique, they were able to find a single marked element quadratically faster than classical heating time. The problem for multiple marked elements is still open. And finally, they were able to combine these ideas of interpolated Markov chains, Szegedy walks, and a new technique from 2019, quantum fast forwarding by Appers and Salet, which is able to speed up sort of classical random walks. I prepare a state that has to do with a classical walk. So this is actually the discriminant matrix that I'm going to talk about later, but you can see it as P. So it's able to apply P t times with complexity square root of T. Okay. So these, let's say, are the main techniques that led to this work, and I'm going to go through them. So, and I hope the next slide answers Alessandro's question. So how do we quantize Markov chain a la Szegedy? So we have to go to a bigger space. So now, before in the Childs and Goldstone algorithm, we were still in a Hilbert space of dimension n, which was the height of the graph. Here, we go a bit in a larger space. So we need a quantum space that has, access from the state space of the Markov chain. We need some extra reference state, 0. So this is our Hilbert space H, and then we're living sort of in H tensor H. Okay. And so Szegedy assumes that we can prepare this sort of state. So from some reference state X, from X and then some reference state 0, we are able to access a unitary that can prepare sort of a superposition or a weighted superposition of the edges of the Markov chain, right? So we have access to this element. And from this states, we define a reflection operator. So pi x by x, so sum over all x's, it can be constructed like this from the projection on the reference 0 state here. And we also need a swap operator. So it swaps the registers if xi is an edge, and it doesn't swap otherwise. So given all these definitions, then we construct the Szegedy-Walk operator in terms of the swap, sort of a reflection around this space of the superposition of edges. Okay. So I don't know if I answered your question, Alessandro. So this is sort of the access model we need for the Markov chain. Okay. And so we can see this operator as sort of a discrete time quantum walk on the edges of a Markov chain. I will say what I mean by this. And also the interesting thing is that we can relate the eigenvectors and eigenvalues of this operator with those of P. I won't go into a lot of details about this, but for example, if you compute the matrix element, something like this, so you can think of BA, quantity BA, as an edge going from A to B. And you can see that if you apply the Szegedy-Walk operator, there's some amplitude to transition for a state CB, whereas you can see this as an edge going from B to C. So in that sense, you can sort of do a quantum walk on the edges of the chain, okay? Because you can transition between states that you can look at as edges. Okay, so for example, with respect to the spectrum, there's a very important property that we have an eigenstate with eigenvalue 1 that encodes the stationary state of the original Markov chain. Okay, so we call this square root pi because now the amplitudes have to have a square root for the state to be normalized in L2 norm. But these are just the entries of the stationary state of the original Markov chain, this pi x's. Okay, so we have this interesting property, and we have other properties that I won't go in a lot of detail about. But okay, so let me now introduce this idea of interpolated Markov chain that was important to develop this algorithm. So again, this was our random walk search algorithm. We prepare pi, we check, and we update according to the Markov chain. So this algorithm, you can see it. It's the similar. So the running time of the algorithm is the same as if you consider an absorbing chain. So what is an absorbing chain? Basically, this means that if you hit the marked node, you won't leave. You stay there. Okay. So you basically remove the edges that were connected to, that were going out of the marked node, okay? And you replaced it by loops so that you stay in this node if you hit the node, okay? So this is the definition of the absorbing chain. And now an interpolated chain is something in between. So you just interpolate between the original chain and the absorbing chain. So you sort of, you can control the strengths of this outgoing nodes and of this loop. And for example, one of the interesting properties here is that, so if S goes to 0, then you recover the original Markov chain, of course. So you have the stationary state pi, which you can decompose into pi u and pi m, so the unmarked part and the marked part. And if S goes to 1, then you are only, your stationary state tends to a state that is only overlap with the marked part, okay? So this property is inherited by the Szegedy-Walk. So now we can construct the Szegedy-Walk for a certain parameter S for the interpolated chain. And so if we go to S going to 0, then the eigenstate with eigenvalue 1 of the Szegedy-Walk encodes the stationary state of the original chain. And the eigenstate with the eigenvalue 1 encodes the state which has only overlap with the marked nodes, if you go for S going to 1. And the interesting thing is that if you are somewhere in the middle, you have a state that has a large overlap both with the stationary state and with the solution state, okay? And so this is the crucial idea that they use in this algorithm 2016. So they combine this with phase estimation. So they choose an appropriate S, like some S star, such that this eigenstate has a large overlap with both. And so if you're able to prepare your initial state to be this one, now you can use quantum phase estimation to sort of do a projective measurement on a state that has both large overlap with this state and this and the marked space. And this way you can find a marked node. But you don't get this general quadratic speedup. So I'm not going to go into a lot of detail here, just to know, for you to know more or less what are the techniques involved in this work. All right. So the final technique that I wanted to talk about is this idea of quantum fast forwarding. And so this was a paper by Simonin, Perzal, and Sarlet. And the idea is that, okay, first, let me define what is a discriminant matrix. So this is a symmetric matrix related to the Markov chain. And under the properties that we assume of ergodicity, reversibility, and so on, then you can show that these are the same eigenvalues as P. So you can sort of think of this operator as P itself, as the spectrum is related and the eigenvalues are actually the same. So what they realized in this work is that D of T, D to the T, so we can think of this as T steps of the classical walk, can be written as a linear combination of unitaries of the Szegedy walk operator. And you can actually truncate the linear combination of unitaries in a number of steps that is proportional to square root of T, okay, times some log 1 over epsilon, where epsilon is some error parameter. Okay, so if you're familiar with the algorithms to implement linear combination of unitaries that were developed also in the context of Hamiltonian simulation and so on, then there are very standard techniques to apply these things, as long as you know how to write them as a linear combination of unitaries. And so this means that you're able to prepare a state which has a component. So if you post-select on some reference state 0, or if you do amplitude amplification on this 0, then you can prepare a state d to the t applied to some initial state phi in a time that is, square root of t. Okay, so we have this quadratic speedup in a sense. Of course, a bit more tricky because this is not a unitary operator, right? So you can have less.
Small question. But so, like in this case, the speedup comes from the fact that we can truncate up to t prime. It doesn't come from an amplitude amplification.
Exactly. Yes.
Huh. Okay.
Yeah. So then so they give a procedure to implement this, and this is going to be important. And in the algorithm that was developed by Ambani's et al. So what is the algorithm? The algorithm itself is simple. I mean, this looks a bit dense, but there's nothing much there. So the idea, okay, we assume that we have a procedure to prepare the stationary state and some reference state. Now, in this state, we check if there is a marked element or not. Like we do actually a quantum way of checking this. And so if there is a marked element, then of course we measure and output the marked element. We measure the first register and output it. If there is no marked element, then this means that the state we're preparing is a superposition of over the unmarked space. Okay, so this is just the first step. It's nothing much. And now the idea is to use this fast forwarding technique. So with fast forwarding, first of all, we're always talking about interpolated chains. So we're using the Szegedy walk of an interpolated chain to do this fast forwarding, as I was mentioning here. So here, this W to the J is the J steps of Szegedy walk of the interpolated chain. And so we use the fast forwarding technique to prepare the state. And actually, there's a procedure to choose a random S specifically. It's not uniform, but it's written on the paper how you choose S. And T, you can choose uniformly between 0 and T, and capital T, where capital T is of the order of the heating time of the Markov chain. Okay. And because of fast forwarding, you can produce this state in a time that is proportional to square root of the heating time. And then the crucial step now is to show that if you measure the first register, there is a sufficiently large probability of finding a marked node. Okay, and it's slightly non-trivial, but they were able to show this. So for this random choice of S, this random choice of T, or you can have a probability, an expected value of the success probability of finding a marked node in this first register, which scales as 1 over logarithm of the heating time. And as I said, this is not trivial at all to show, and this was the main result of this paper. All right. So I don't know if you have any questions up to here. Okay, so I'll go on. Right. So the question we pose ourselves is that, okay, I mean, this can be done in discrete time. So in principle, it should also be possible to do in continuous time. But how do we do this, right? Because there is no general translation. And we thought that in the way of doing that, we'll find some interesting things. And so if we look at the main tools that were used in Ambanis et al., so there was the Szegedi walk, so the discrete time quantization of these interpolated Markov chains. And this was this idea of fast forward, okay? These were the main techniques. Now, okay, so this was the Szegedi walk operator, which is a sort of a discrete time quantum walk on the edges of Markov chain. Now, what we would like is to have a Hamiltonian that defines a continuous time quantum walk on the edges of the Markov chain, right? And so this actually exists. So this idea was introduced by a paper Soma and Ortiz in around 2010. And so they are able to use these unitaries and so on to construct an emission matrix that you can see as a Hamiltonian. And using a similar argument, you can think of this as the continuous time quantum walks on the edges of the Markov chain. And the spectrum of this Hamiltonian is also related to the spectrum of P in the following way. So again, let us look at the discriminant matrix of P. So the eigenvalues are lambda k, the same as P. The eigenvectors are Vk. And so you can show that this has an eigenstate with eigenvalue 1 Vn. So here I'm writing in the cat notation, but this is just a classical thing, right? This is the discriminant matrix of a Markov chain. So this is the stationary state, the eigenvalue with the eigenstate with eigenvalue 1. And so we have the stationary state pi, and we have a spectral gap here of delta, okay? So it's 1 minus the second largest eigenvalue. Now, the Soma-Ortiz quantization Hamiltonian as the following relevant subspace that I mean, our dynamics usually is always contained in the subspace when you develop quantum algorithms with this approach. So here, these VKs are sort of mapped by two pairs with some VK0 and some orthogonal state to this state. And the eigenvalues, so each of these eigenvalues here is mapped to a pair of eigenvalues, so plus or minus square root of 1 minus lambda k squared. And again, we have this property. Now we have an eigenstate with eigenvalue 0, which encodes the stationary state of the Markov chain, of the original Markov chain. And so we have also this important property, which is a spectral gap amplification. So here, around this 0 eigenvalue, we have these two eigenvalues, which are, you know, square root of delta and minus square root of delta. So there's this property of spectral gap amplification that is important also to develop. All right.
Sorry, what do you mean exactly by spectral gap?
Yeah, I just mean that where the original Markov chain, the gap delta, here your Hamiltonian is a spectral gap square root delta. So delta, if it's a small number, square root delta is going to be quadratically large. Okay. And yeah, so for example, with this quantization, this suggests an adiabatic algorithm for the search problem. How? So this was the idea in 2010 of the adiabatic algorithm. So we start with the initial state that encodes the stationary state of the original Markov chain. And now we do an adiabatic evolution over this parameter of the interpolated Markov chain. Okay, so this is the interpolated chain between the absorbing chain and the original chain. And so by evolving this parameter, we can sort of transport this zero energy eigenstate, which is square root of the stationary state now of the interpolated chain. And so we can sort of change this state and transport it all the way to this state, which is a state that is overlapped only in unmarked space, okay? If we do it slowly enough. So this is just the stationary state of the interpolated, of the Hamiltonian, right? As a function of S. So you can see it interpolates between the unmarked space and the marked space, okay? I won't go into the details about these things, but these are also simple expressions for these angles. Okay, so the problem here is that, okay, we have a running time that, so they were able to show that the running time of this adiabatic approach scales as the square root of the the extended heating time, okay? And the extended heating time, I'm also not going to define, but what I want you to know is that for a single marked node, this is the same as the heating time. So this gives a quadratic speed up for the single marked node case. And for more than a single marked node, then this is larger or equal than the heating time. And actually in the Ambani's et al. Paper, they were able to show that it can actually be much larger, the extended heating time, than the heating time. So they give a specific example where this can be much larger. Okay, so the adiabatic approach does not fully solve the problem for multiple marked vertices, but we can borrow this idea of using this Sommer-Ortiz quantization for the Hamiltonian. So we want to define a continuous time walk, which involves this Hamiltonian. But now, what is the second technique that was important was this quantum fast forwarding, and there was no such thing as continuous time quantum fast forwarding. Okay, so let's see what we can do about this. So we actually developed a way that can be seen as a fast forwarding of continuous time random walks. So the first observation to develop this is to realize that if you apply this, let's say this Hamiltonian to some state size 0, you get basically identity minus the discriminant matrix squared. Okay, and if you remember, the discriminant matrix has the same spectrum as P, same eigenvalues. Okay, so if I was able to apply e to the minus th squared for some reason, then I would be able to apply, and then this would be equivalent. Sorry, this would be equivalent as applying e to the d squared minus identity times t. Okay, and this you can see as a continuous time random walk associated to p squared. So yeah, this operator actually conserves probability if this was a continuous time random walk. So this is a valid continuous time random walk. Here we have d squared instead of p squared, but as they have the same eigenvalues, we can sort of see this as a continuous time random walk associated to p squared. Now, okay, so are we able to implement this quadratically faster, right? And so to do that, we use this Hubbard-Stratanovich transformation, which was used also in different works by Roland Sommer and other people. And the idea is to write this operator. So you can see this as an imaginary time evolution under h squared. And you can write this as an integral over some coefficients here. And here you have like the time evolution under real time. So z so this you can see this as a Gaussian with a fixed standard deviation, right? This is a Gaussian, and here you have like the usual time evolution operator, right? And you see that here you have a square root of 2t factor appearing, and if you actually discretize this operation, you can think of this as implementing this operator that you want to implement as a linear combination of time evolutions under this Hamiltonian. Well, in general, this is valid for any Hamiltonian, but of course, we'll be interested in implementing this Hamiltonian that's related to the original chain. Okay. So yeah, this Hubbard-Stratanovich transformation gives us also a linear combination of unitaries, and using similar arguments, you can actually show that you can truncate this at some j, some capital J, and so that the maximum evolution time that you need also scales the square root of t log 1 over epsilon. Okay, so we have this fast forwarding property. Okay, so to evolve the continuous time walk, random walk for time t, we only need square root of t operations. Okay, so this seems to be the right way to go, but we have a problem is that, so to actually implement linear combination of unitaries, we need in general to have more than just simple time evolution, right? We need the ancillary spaces, and we need some controlled operations and this linear combination of unitaries algorithm. So in general, a linear combination of unitaries, as I said, would allow you to prepare a state of this form. But we will need some controlled operations between this extra register and so on. But we do, our assumption is that we just want to evolve under the Hamiltonian, right? This was our assumption here. We want to have just a purely continuous time random walk algorithm. Yeah. So yeah, but there's a simple realization that you can do. So you can actually, if you're just interested in measuring this state. So I want to make a projective measurement on this state here, which is what I want to do because we want to see whether we can find a marked node or not. So in this context, you can actually replace the procedure to prepare this gamma LCU, so the state from the combination of uniters. You can replace this whole thing by just considering a randomized time evolution. Okay, so these operators are the same. So this is the time evolution, the same that appears here. But now instead of applying, let's say, a superposition of time evolutions, we just apply time evolution randomly. And these PJs are related to these coefficients of the linear combination of unitaries. Okay, now of course they have to be normalized. Okay, so if you prepare the state randomized and you measure, you check whether there's a solution or not. So you make you compute the probability of measuring a marked element in this row state. You can show that it's actually larger than if you did the same in the linear combination of unitary state. Okay, so so this somehow allows you to do projective measurements in this state without doing the whole complicated linear combination of unitary thing. Okay, so this was the, let's say, the crucial idea to sort of get rid of the linear combination of unitaries and replaced by random time evolution with a quantum walk. And this idea was also observed in a later paper. So after the Ambani's et al. Paper. So they have a unified framework of quantum walk search where they unify different formalisms of discrete time quantum walk search. And they also observed this idea here. Okay, so putting all this together, so the first step of our continuous time quantum algorithm is the same. So we assume a procedure to prepare the stationary state, quantum encoding of the stationary state, the original chain. We check. We assume most likely we're not going to be able to find a marked element because we assume there are a few of them. Otherwise, the problem is easy. And so then if we don't find, then we are preparing the state, which is overlap only on the unmarked space. Now we have this analogous to the quantum fast forwarding thing, but now in continuous time. And the idea is simply to prepare these randomized time evolution states. So these TJs are picked at random according to these PJs, which I defined before. And here, the crucial step is we only need the TJ to scale maximum as square root of the heating time. And then comes also the hard step is to show that now if we measure the state, also we choose S randomly, right? So if we measure the state, we're able to obtain a marked element with a high probability. And so also we need quite a few technical steps, plus some lemma that we borrow from the work of Ambani's et al. To show that the success probability is 1 over log square of the heating time. Okay. So this is the way that we can obtain these general quadratic speedups now with the continuous time walk. And so somehow as a spin-off of this work, it was just this simple realization of a procedure to prepare this state. And we believe that this could have other interesting applications. So for example, for ground state preparation. So if T is large enough, this actually would apply approximately a projection on the ground state of H. And so one could think of an easy procedure inspired by this Hubbard-Svratanovich transformation, which, well, if you look at this from a physics perspective, is very simple. If you look at this from a computer science perspective, all you have to do is like to discretize this and write this Gaussian state. So as in terms of qubits, as a discrete space. But if you look at this in a physics perspective, the algorithm would be very simple. So you have some discrete system psi, you couple it to a continuous system which is in a Gaussian state. So this could be seen as the ground state of the harmonic oscillator, which is, let's say, one of the most common states studying quantum mechanics. Now you have a coupling Hamiltonian, so between H and the position operator of this continuous system, okay? And so you couple these two systems with this interaction Hamiltonian 4 times square root of T. And then you simply post-select on the continuous system. So you measure in the, I'd say, in the eigenbasis of the harmonic oscillator. And if you see again the ground state, then you know that on the other register, you have prepared this state, e to the minus t h squared, okay? And so for t large enough, as I said, you can approximate the ground state of the Hamiltonian here. And if you do the complexity analysis, you can actually show that this procedure has the same complexity as other similar procedures that are slightly more complicated conceptually because they need linear combination of unitars and so on. So if you discretize this, you would also need a linear combination of unitars, but somehow, we believe this procedure is sort of conceptually simpler, even if when you do this in the circuit model, you'll probably do something similar to other algorithms. But maybe these sort of ideas can lead to other results in the future. And also this idea of getting rid of the LCU means that if I just wanted to measure now something related to the LCU state, I could just consider randomized time evolution instead of preparing the whole thing. So I could get rid of this ancillary register. So all right, so more or less at the same time, there was also other papers that realized this. So this was published a few weeks before our paper, these two works, which also use Hubbard-Stojanovic transformation and so on to prepare ground states and to implement this sort of operators. Okay, so this seems to be interesting techniques for ground state preparation. So just a summary, I believe I have 5 minutes, but I'll summarize so that there's time for questions. So quantum walks are natural ways for tackle such problems. There have been a lot of different approaches. So in continuous time, there was a simple approach by Charles and Goldstone that was not able to provide general quadratic speedups with respect to classical heating times. And then we used this more general approach to finally close the gap between the performance of continuous and discrete time approaches for the search problem, okay, which was an open question. So thank you for your attention, and I'll be happy to hear your comments and questions.
Thank you for your talk. Exactly. So I was a little bit lost with this transformation.
The Hubbard-Stojanovic.
Yeah.
Yeah, so this is just a mathematical trick in a way. I think you can, the way to derive it is that you look at the eigenspectrum of H, right? So if you put an eigenvalue here, this is just a transformation on numbers. And I think this just follows from, doing a Fourier transform of a Gaussian. So if you think of this as a number, basically, I think this is sort of the statement saying that the Fourier transform of a Gaussian is a Gaussian. If you see this, there's like a Gaussian here and there's a Gaussian there. This is sort of where it comes from. But if you think of this in terms of operators and you discretize it, then you can think of this as a way to prepare this operator in terms of a linear combination of time evolution. I don't know if it was clear. So it was more or less to make the analogy with the fast forwarding method, where here you have a linear combination of Szegedy walks.
Yes.
Up to time square root of t. And now we want to replace somehow this Szegedy walk by a Hamiltonian evolution, right? Because we're in continuous time. And so this is somehow what we achieve with this transformation. Although it's a little bit more cumbersome because we have here H squared that is sort of related to the continuous time random walk associated to P squared. So yeah, this we needed to do some extra technical steps, to convert P squared to P and so on when you're proving the final amplitude here. But
So in some sense, the technique was to find a continuous way to approximate the time evolution of e to the minus th squared.
Yes. Yeah, this is imaginary time evolution. which because of this property of the Hamiltonian, we can relate it to the continuous time classical walk. Yeah. Yeah, it's not good. Maybe there are other ways to do this. This was like the way that we found, but there might be other completely different ways to go around this problem.
So I noticed the adiabatics still open, right?
Yeah, so we haven't looked at it yet. In principle, yeah, I don't know actually whether there's an easy way to prove that the adiabatic also works on square root of the heating time.
I mean, my feeling is the continuous time when run the walk is closer to the adiabatic one than the discrete, right?
Yeah, yeah, definitely.
Maybe I don't know, do you think you can use these techniques to have something for the adiabatic?
Yeah, I don't know. It's a bit difficult because here we sort of the known results you have to randomize over S. So somehow what the continuous time walk is doing is like just to pick an S randomly on this line in a specific way and just evolve according to that S. So we don't change S in time. I don't know what would that would translate in the adiabatic case. Maybe somehow you need to adapt the adiabatic schedule in a different way, you know. Yeah, I haven't really thought about this. In a way, the continuous time procedure is simpler, right? Because you just have a time-independent Hamiltonian. But maybe by thinking about how to translate this to a adiabatic setting, one could, come up with interesting realizations that also could be used in other contexts. I don't know.
Right.
Did it?
Okay. Doesn't seem straightforward.
Yeah, I don't see a direct way to translate it. But well, yeah, I guess one would have to look at how the spectrum evolves with S. I don't remember exactly this, but I think this is known. Yeah, let's just think of it.
Right. Yeah. It's you don't evolve with S, right? You just pick one.
Yeah, in the continuous time case, we just pick one. Yeah. But I don't remember if in the adiabatic case they have to sort of adapt the way they change S with time, because sometimes you have to go slower in some parts where you have smaller gaps and faster where you have larger gaps. So I don't remember. Maybe they have to do something similar here. And if that is the case, then we could sort of, and so typically you go slower where there's like an avoided crossing.
Right.
So I don't know what would be the equivalent. Maybe you could think that you assume that the avoided crossing is that some random S, and some random S star, and do the adiabatic schedule, assuming that the avoided crossing is there. I don't know.
When you pick a random S, do you then evolve? You get the pi state using adiabatic, and then use this pi state for the rest of your algorithm? I don't know if I understood correctly.
You mean in the adiabatic case or in the continuous?
In the continuous.
So yeah, in the continuous, we assume we prepared this state, so the stationary state of the original chain,
and you evolve,
and then you evolve according to a random S. But you don't assume that you can
using adiabatic evolution.
No, using like a time independent.
Okay.
Right. So here your H is for a fixed S. It does not depend on time. So yeah, so you pick so maybe let's go here. Yeah, so here you pick an S, and so this is actually H of that S that you picked.
I see. Fair
H of the interpolated Markov chain for that S.
Okay. Right.
I should have written H of S to be clear. Yeah.
Okay.
Yeah. Well,
cool, yeah.
Thank you so much, Leonardo.
Welcome, thanks for inviting me. I gave an overview.
That was nice. Yeah, it was nice.
Super cool. Super cool. Yeah.
Because I've seen the 2020 version talk.
Yeah, true.
can
Yeah,
see-
we had like
see- See how it evolved.
Yeah, it evolved a little bit with this fast forwarding and so on. But I guess
Yeah.
a lot of the slides are sort of similar. But yeah, the main new thing is like, yeah, this fast forwarding technique and like the server Stratanovich and so on.
Mhm. Oh, that's cool.
Okay.
Well, so
Wait, there's something in the chat. Okay, there's just
uh,
thank
let's thank the speaker.
you. Thank you, everyone.